Okay, hi, welcome to the second part of this first lecture, lecture 1.2. Um, we now want to get to a pretty major point about linear combinations, which we'll get to in a second. First, I just have a definition. It's really more notation. If you just see a zero, sometimes we put an arrow over it to alert you that it's a vector, but sometimes we'll leave it off. The book leaves it off a lot. But from context, if we know this should be a vector from some equation, say there's n of these zeros, so it's in Rn, this is just a zero vector. That's what this means. So we'll just write zero sometimes. All right, so the next step is to make the jump. We know how to compute a linear combination. We know the rules of scalar multiplication and vector addition. So now the question is, what is the set of all linear combinations? So this is called the span. So let's give a definition of this. So definition. Now let's suppose we have actually k vectors. So suppose we have k vectors in Rn. And let's call them let's say V1. So before these were the elements, now they're the vectors, okay? So Vk. So these are all in Rn. They each have n elements in them. Okay? Then the span of these vectors, V1, Vk, which we'll sometimes write like this with these straight brackets, is just equal to all linear combinations of these vectors. So I can use whatever coefficients I want and then add that together. So this is equal to, so how would you write that? Summation, say I equals 1 to k, and then ci vi for bunch of c's, right, in the real number, for ci, bunch of real numbers, ci, I equal 1 to k. Okay, so this is the span. So as long as the CIs are in R, I have this. So it's the set of these sums. So this is equal to the set of these sums like this. Okay, so all right. So for example, in R2. We could maybe use it a little simpler. Let, say, V and W be in R2. They each have two elements. And then the span of V and W, it's everywhere linear combinations of V and W can go. This is just equal to, say, the set CV plus DW such that C and D are real numbers. Okay. All right. So starting here in Rn, we can see we can generalize this. So we're going here to R2. I have V and W, and I have defined something called the span. So the question is, what is the span? And what do you think? This depends on V and W, right? It depends on V and W. But it's actually not too hard to classify the possibilities here. So let's ask this question. Describe VW. Okay. And here I draw this little picture of R2 here. It's just, I don't know why I did it, but I think I'll need it in a minute. Yeah, okay. So what is the set of all linear combinations of V and W? Well, it falls into three cases. Case one is kind of a silly case. This is if so let's write if V equals W equals the zero vector. I can put an arrow for now. Then all linear combinations of V and W are what? So then span of V and W is equal to a set of vectors. It's just equal to the zero vector, right? I don't need to put those curly braces there. It's just one vector. But if you want, you can put them. Okay, so that's obvious, right? Because if I take any number times v plus any number times w and add them together, I get the zero back. Okay, what if, say, v is not equal to the zero vector and w is a multiple of v? So w is a multiple of v. W equals CV for some c, okay? Then what do you think you get? Well, then, it depends what v is, right? But then, VW, whatever it is just equal to the span of v. It's just along the line that is in the direction of v, or the negative direction. So it's just a line in direction of plus or minus v. Okay? Does that make sense? So for example, if we want to see an example of this, to see an example of this, for example, suppose v equals 1, 3, and w equals 3, 9. Then the span of v and w is equal to the span of v, because if I have any two real numbers for c and d in R, we have CV plus dw is just equal to, well, look, w is just 3v, right? So that's CV plus d 3v. And now I can factor this 3d and the c outside too. So I get c plus 3d times v, which is clearly in the span of v, right? Because it's just a multiple of v. Okay, so for any CD in R, this is in the span of v, so span of VW is equal to the span of v. All right, so VW, the span of VW is a line in this case. I want to make sure I don't go too long. YouTube doesn't like super long videos. So. Okay, finally, so that's 2. I can have a point, or just a degenerate vector that's just 0, 0, the 0 vector, or I can have a whole line of vectors. So that's the first one. Second one is a line, right, along v. And it keeps going, though, infinite. So, by the way, this case 2, is an infinite set already. It's just along a single multiples of a single vector. Okay, the second case, suppose suppose v and w are not equal to 0. Okay, so, or v is not equal to the 0 vector, and w is not a multiple of v. Well, then I get, I don't get a line, I get the whole plane, okay? So then VW is equal to all of R2. I get any possible, they span every possible vector in R2. So I could do a proof of that, or I'll just do a little example for now. So example, suppose we have v equals 1, 0 and w equals 1, 2. Then I claim that these are not multiples of each other. At least one of them is non-zero, so VW, they're both non-zero, is equal to R2. All right? So to prove this, I will just show you that I can find a linear combination that will equal any vector. Okay, so to show this, show it. Okay, so to show it, we'll just say CV. I can write this in now, plus D12 equals B1, B2. This is B. Okay, so we're going to show CV plus DW is equal to B for any B in R2. So if I can find a linear combination that equals some arbitrary B that's not specified, then this is a proof that I can find a linear combination of V and W for any vector in R2, and therefore the span is all of R2. So, so could we find the C and D? What is it? Well, you see this equation came out easy. I didn't intend it, but this one's 0 here. So I have 2D. I can set, so yes, we set D equal to B2 divided by 2. See, if I set that, then the bottom equation is correct. And I set C then equal to, substituting in B2 over 2 for D, I get B1 minus B2 over 2. And yes, two vectors are equal when the corresponding entries are equal. All corresponding entries are equal. Okay? So I needed that when I added these together, which I do by first multiplying and then adding them together, is equal to this, right? So like this over here, actually, like if I were to take more steps here, I would have the top entry would be C plus D. So I'd have C plus D on the top, and on the bottom I would have 2D. So that, and then you can see that, yes, this is true if D is set equal to B2 over 2. And I can see, let's see what time it is. I can see that this will be okay graphically too. But I should stop now. So that will be on the next lecture.